In this video, I am going to discuss relation between electric field and electric potential. In earlier video, we have discussed about the electric field, electric potential, electric dipole, superposition principle. Okay, now in this we'll study how this electric field and electric potentials are related. So far we have seen, let us say if there is a point charge Q and say this is point A and this is point B. If we take this distance to be R1 and take this distance from point charge Q to point B is R2, so we have defined VA minus VB, that is potential difference between A and B, is also equals to UA minus UB, that is change in potential energy between point A and point B divided by the magnitude of the test charge, which is also equals to work done in moving a test charge from B to A divided by magnitude of the test charge, which is also equals to Q over 4 pi of epsilon naught 1 over R1 minus 1 over R2. Now, just use this for a very small change, very small change. We can write this VA minus VB to be dV, and UA minus UB could be written as it's a du. So dV is equals to du upon test charge. dV is the change in electric potential and du is the change in electric potential energy. We know that du is negative of the work done, so this expression can be written as dV to be equals to its minus of dW over Q naught, which is also equals to F dot dr over Q naught. This F again further can be written as it's a E into Q naught dot dr upon d Q naught. Since what is electric field, how we define, if you remember, this is force per unit test charge, so the force could be written as a Q naught into E dot dr. Q naught will cancel out and we get that dV to be equals to it's a minus of E dot dr. That's an important relation between electric field and change in electric potential. dV is equals to minus of E dot dr. Now we can discuss different cases in it. Say case 1, which is maximum asked in the CBSE board. dV, if V is function of x only, that is it's varying only in one direction, that is potential varying only in one direction, then the dV when can represent it's a minus of E dot dx or simply E dx. How? Because this, if you see, let's make it another case too. If V is a function of x, y, z, right? So E would also be the function of all three. That is, E will be a function of also x, y, z. Okay, so we can write then E in vector form, that E will be it's a Ex I cap, Ey j cap, and it's a Ez k cap. The same way, the dr vector could be written as it's a dx I cap, dy j cap, and plus dz k cap. So that E dot dr, that means it becomes dV to be equals to it's a minus of it's minus of ex dx, because I dot I becomes 1, plus ey dy plus ez dz. This, you can say, this is a general expression for relation between electric potential and electric field. Now you can say, coming back again to the, if v is a function of x only, if v is a function of x only, now again I'm writing the case 1, if v is a function of x only, right, then you can neglect this. Yani what you can write, that electric field along x-axis is, it's a minus of dv upon dx. That means a potential is given and it's varying only in one direction, that let us say along x-axis, then electric field along x-axis will be, it's a negative of the potential gradient. So this is important statement. We write electric field is negative of potential gradient. Gradient, here gradient means variation with respect to distance. Now suppose, let's take some example. Say for example, v is given as, it's a x square plus 7, this much volt. Now here you can see v varying only along x-axis. Now the question comes, find electric field, say at x equals to 1 meter. So how we'll do it? We'll say E is equals to, it's a minus of dv upon dx, which is minus of 2x plus 0. Now we want electric field at x equals to 1 meter, that's a minus 2. What? It's a volt per meter, or minus 2 Newton per coulomb. You can also say that electric field is 2 volt per meter or 2 Newton per coulomb along negative x-axis. You see, one more interesting thing is, unit for the electric field, is, as we know, it's a Newton per coulomb, and by this relation you also know that it's also volt per meter. Now take some different question. Let us say here voltage was given and I ask electric field. Now suppose if electric field is given, how we can write voltage? Say if E is equals to, say, E naught x I cap Newton per coulomb, find potential at x equals to x naught if it is V naught at origin. Okay, now here see, one can see that electric field is a function of x only. So we'll write that dv, since dv is equals to, it's a minus of ex dx, which gives you that dv to be equals to minus of e naught into x dx. Integrated, since e naught is common, take it out. This is v to be equals to minus of e naught into x square by 2. Let's say plus c, either you put the limit or put some integration constant c. Now it's given that v at origin, that is at x equals to 0, it is given as v naught minus, it's 0 plus c, that implies c to be equals to v naught. So the general expression becomes v to be equals to minus of e naught x square by 2 plus v naught. So the potential at x equals to x naught, it would be, it's a minus of minus of E naught into x naught square by 2 plus V naught. So in that way, if the potential is given, one can find electric field, or if electric field is given, one can find electric potential. Now the questions comes, suppose if V is a function of, let us say, more x, y, z, then how we do it? Take this case. If V is a function of x, y, z, so as we know, then we can write dv to be equals to, it's a minus of ex dx plus ey dy plus ez dz. Now suppose if we want to write ex from this, so how will write ex? Now if this 2 is not given, it's only function of x, then we'll write ex to be equals to minus of dv upon dx. If this is not given, then we write ey to be equals to, it's a minus of dv upon dy. If all three are given, then how we can write ex? We have to do it partial derivative, that is del v over del x. Del, this symbol is used for the partial derivative. And what is the partial derivative means? It's a simple differentiate v with respect to x, keeping y and z as a constant. So it's a simple derivation. Suppose if we want to find ey, differentiate v with respect to y, keep xz as a constant. Same way, ez, this is minus of del v over del z, keep x, y as a constant. Now, let's take an example. Suppose v is equals to, it's a x square y plus y square z plus z square x, this much volt. Here you can see, here question says v is a function of all x, y, z. It's a varying in 3 direction. Now the question is, find electric field. Find electric field at point 1, 0, minus 1. Find electric field at point 1, 0, minus 1 if potential is V naught at origin. The potential is V naught at origin. In fact, this is not required. Let us say first we'll find that potential. This statement is not required. Okay, let's say we'll discuss this further. First, you just do it. V equals to x square y plus y square z plus z square x volt. Find electric potential at point 1, 0, electric field at point 1, 0, minus 1. See how we'll do it. First we find electric field along x-axis, that will be minus of del v over del x, keeping yz as a constant. So if you differentiate this, this comes out to be, it's a minus 2xy plus 0 plus z square. If we put this value at point 1, 0, minus 1, this will come out to be, it's a minus, z is minus 1, that's a plus 1, and this is comes out to be, it's a minus 1. Similarly, if we find ey, this will be minus of del v over del y, keeping xz as a constant. If you differentiate this expression, so this will come out to be, it's a minus, it's a x square plus 2yz plus 0. So that ey at a point 1, 0, minus 1, it comes out to be minus 1 plus 0, that's a minus 1. Now the same way, get Ez, this is minus of del V over del Z, differentiate V with respect to Z, keeping xy as a constant. This comes out to be, it's a minus of x, that's a 0, plus y square plus 2zx. And if we substitute the value, that Ez at 0.10 minus 1, it comes out to be, it's a 0 plus 2zx. That makes it's a 2 minus 2, which becomes plus 2. So you see, electric field along x-axis comes out to be minus 1, along y-axis comes out to be minus 1, and for z-axis comes out to be 2. So can write that electric field in vector form. This is minus I cap minus j cap plus 2 k cap, because it's 1 Newton per Coulomb along minus x-axis, 1 Newton per Coulomb along minus y-axis, and 2 Newton Coulomb along z-axis. If we want to write its magnitude, this comes out to be the square root of 1 plus 1 plus 4, that's root 6 Newton per Coulomb or volt per meter. If you like this video, don't forget to like and subscribe the video. Thank you.